Hello, everyone. It's my great pleasure to introduce to you our today's speaker, which is Gabi Katatsova. She's a PhD student at the Charles University in Prague, working on neural architecture search, specifically with the focus on performance prediction, using zero-cost proxies and working on graph neural networks. And today she will present our work on GRAF, performance prediction with neural graph features. And I'm very happy to have her here today talking about her work / our work. I'm really curious and excited. And the stage is yours.
Thanks, Yulita, for the kind introduction. So, as Yulita said, I will talk about neural architecture search and shortly introduce in a few slides what's it about, so performance predictors, zero-cost proxies. Then I'll move to the main topic, which is GRAF and its results, and then also quite a lot on future work and overall discussion about what may be good, how to apply it. And if we still have some minutes left, then I also have a collab example that was originally presented at the OpenML conference this year, also with Yolita as a tutorial. And yeah, let's get to neural architecture search. How to start a talk about neural architecture search? Well, the best way is to show this nice plot. So many of us probably already know it. So we need to have a search space, and then it's about searching via search strategy and with performance estimation strategy, which is the focus today. So more specifically, performance estimation has many specific forms. What we are talking about is model-based prediction. So you train a surrogate with pairs of architectures and their performances, which can be either, for example, validation accuracy or perplexity, or it could be other tasks like hardware tasks like latency or energy, robust accuracy, etc. You train the surrogate and then you pass a test architecture and you will get performance for free. For supernets, you can kind of imagine it as just having the bottom row. So you already have a trained supernet and basically the predictor is doing the evaluation with inherited weights. Which is quite good because you don't need to train the architectures to get the actual performance. So we could ask ourselves, why should we even use model-based performance predictors when we've got the supernets? So that's just one training that must clearly be better, right? There are some catches here. So one is that if you have a very, very flexible search space, for example, like Einspace that was presented in a few weeks, maybe a month ago or so, you can't really build a supernet, or it will probably be very hard because of how different the architectures are. So if you want to somehow make the cost smaller, so that might be good. Other advantages are that you can easily just integrate that into, for example, BO, Bayesian optimization or evolutionary algorithms. It's pretty easy to do. It kind of also gives you an idea how the search space looks like as a whole. So if you have an interpretable model, which, for example, here GRAF enables, you can kind of get an idea what's happening there. It's not only a black box. And in more, like, it's not supernet or a model-based predictor. You can also combine it, and people do that. So for many super networks like HAT, hardware transformers, OFA, all of these have a hardware surrogate to avoid just like, even though it's cheap, maybe you don't want to do it for all the 10,000 of architectures that you've got. So a predictor will make that easier for you. And also models-based predictors are transferable. So then if you want to transfer to new devices or maybe do some meta learning, there are works on that. It's possible with this, which otherwise wouldn't be easy to do with the supernets. So there's still plenty of reasons why to study model-based performance predictors. But today we'll kind of focus on a different point of view on performance predictors, and that is in form of how to encode architectures for performance predictors. So this is kind of determined by the type of the predictor. So quite often you use tabular performance predictors like random forest, graph neural networks, XGBoost, graph neural networks. No, these are the other ones, but more like MLPs. And usually the simplest form is to just get a one-hot encoding of operations, plus you flatten the adjacency metrics to just get a long list of zeros and ones, and you put that into a predictor. Other option is to use kernels. So for example, in NASPL, there was a Wi-Fi lemon kernel, which also connects quite nicely to Bayesian optimization. So these are kind of more specific to maybe a bit theoretically inspired. Another thing that was in the literature is path encoding that's paired with bananas. So I'm missing a bananas reference here, maybe later. And for that, you get all the possible paths from the input to the output. And then you mark if the path is present in your specific architecture. So that scales really badly. If you've got a lot of possibilities in the cell, then there's a lot of possible paths. We'll also look at how to use zero-cost proxies as an encoding. That will be later on next slides. And then the last thing is the GNNs usually just eat up directly the operation encoding and adjacency metrics. And you would want the GNNs to be kind of good predictors because it's a learnable model. So that should be the state of the art, right? As we will see, no, at least not the GNNs that are used currently in NAS. All right. Now to zero-cost proxies. Short summary, it's a score that's supposed to correlate with validation accuracy. You need just one batch of data that you pass through an untrained network. And then the differences are if they are data dependent, and by data, we mean input data. Like, for example, a batch of cipher 10 versus data independent. That doesn't mean that there's no batch passed through the network, but it means that, for example, a batch of ones. So like a one matrix of all ones that you pass through the network instead of cipher 10 batches. Another another way how you could look at it is you've got zero-cost proxies that require a backward pass and zero-cost proxies that don't require a backward pass. The latter is kind of very fast to compute, but maybe it doesn't capture the properties of the network that you need. And then also the out of the published zero-cost proxies, some were more constrained due to a specific architecture, like for example, NASWOT requires you to have redos in the architecture, somewhere for classification. So this is more like if you want to apply a zero-cost proxy to your problem, this kind of division is something that you want to think about because, for example, if you cannot do a backward pass, then that's kind of tough to apply to zero-cost proxy. Out of the zero-cost proxies, some of them had really quite a good correlation across multiple search spaces and tasks, even though there's not one zero-cost proxy that would work for all the tasks. Why do zero-cost proxies work at all? That's what we'll ask us and answer later in 2 slides, actually, because there's 1 slide versus just some example proxies that you may encounter. Most of them have been studies in NAS Bench 2.0, benchmark of zero-cost proxies and their scores. There were some new, and those are mostly either a combination of existing proxies or like an extension, or for example, some simple with extra steps. So basically, the NASBench 0 has the most common ones. In a few weeks, actually, I think there should be a video of our tutorial with Jovita that we have on at the Autonomous Forum about performance predictors and also zero-cost proxies. So if you want to know more details, you can look at it. Anyway, just a few examples here. It's mostly, for example, analyzing the covariance of the Jacobian to get through the backward paths. Then Fisher just multiplies activation with the gradient, and then there's some summing across spatial resolution. But there are also quite simple zero-cost proxies. For example, L2 norm, that's just summing the L2 norms of the weights, and then flops and params. Those are all kind of baselines. So you can then use zero-cost proxies really in place of the validation accuracy. So instead of having the validation accuracy as your target, you will just use the proxy. So that's, for example, really useful when you want to warm start search, for example, in evolutionary algorithms. To construct the initial generation, you will just get the networks that have the highest score. So it's kind of a filter. Or another application, which we will use here quite heavily, is to have it as an encoding for performance prediction. And the last application, you can somehow add them to graph neural networks to make them better. This actually quite works because it kind of plays well with the weaknesses of graph neural networks. So what GNNs cannot do, zero-cost proxies usually tend to make better. All right, but why do they work? So some of you may already have seen this nice scatter plot. It's on x-axis, that's the validation accuracy, y-axis is the NASWOT score, and it's all the networks from NASBench 201. So as you can see, the correlation is quite good. Like good networks with a good validation accuracy have quite a high score, and it's just overall looks good, except for the clusters. So what could the clusters be? And when we analyzed that for a few afternoons, we realized it's actually the number of convolutions. So each color is a specific count of convolutions. So red is 3 convolutions. The top one has the maximum number of convolutions. And that's why it correlates quite well. And this is the reason also for other zero-cost proxies, at least on MB201. It's not really observable, for example, on darts, where it's just something else happening there. I try to also color it by, for example, the number of separable convolutions or the other type of convolutions. There are related convolutions. It didn't split quite as nicely as here. It's not perfectly steps like in here for L2 norm, but the clouds kind of split into 2 clouds for each of them based on if there's more convolutions 1 by 1 or 3 by 3. So NASWOT is actually one of those proxies that worked quite well, had quite a nice correlation, but this is mainly the reason, at least on the simpler search spaces. So that's maybe the first lesson. If you want to introduce a new zero-cost proxy or somebody gives you a new zero-cost proxy, maybe try to compare that to the number of operations because the proxy may just do that or just be influenced heavily by this. All right. So then we can ask ourselves, like, if operation count is a good proxy, do maybe some other properties work? And we started playing around in Jupyter Notebook and just try to examine if we add this to the prediction, does it make it better or not? What's the correlation? And we came up with a bunch of other features. So mostly it's either operation counts, then path lengths, and then node degrees. So this is a really nice picture that Jovita drew. Thank you, Jovita. And it represents a cell from NASBench 201. So NASBench 201 is a cell-based search space where the same cells repeat multiple times across the whole network architecture. And edges are operations. So for example, in this example cell, you've got a skip connection from the input to the output, then a convolution 3x3 followed by average pooling. And there's also one edge that's deactivated because it's 0. And then for the example features, so for example, the first one is the input node degree, where we count only skip connections and convolutions 3x3. So here, the count will be 2. If we would count only skip connection, the count would be 1. Then for path lengths, we've got minimum and maximum path length. So if it's maximum, we try to, for example, here, go from the input to the output by using as many edges as possible, but restricting ourselves to skip connections. So here it's only 1, but if we restrict ourselves to skip connections and convolutions 3x3, suddenly we can utilize more edges. So here, the length would be 3. If it were a minimum path length, on the other hand, for over skips and convolution 3x3, it would be 1 again, because we can just utilize this edge. So in general, for all the graph features, we compute them for all the operation subsets. So like here, this max path length would be for skip, then for convolution, average pooling, etc. Then pairs, then 3 operations, and just really exhaustively all the subsets. So we've got operation counts, then all minimum path lengths, max path lengths, and then the degree of input and output node, and also adding an average degree across all the nodes. So what's the average number of skip connections that gets out of a node in the cell? A few examples, some of them were already shown on the previous slide. So for example, just minimum path length over all the convolutions or all the skips. So for example, when we've got the maximum path length over convolutions, we can see that kind of as the depth of the network, because we try to get as many convolutions as possible, and that's kind of how deep the network is. On the other hand, the minimum path length, it's kind of if there is a shortcut from the input to the output. So is there a skip connection? So that's kind of a residual counts you the residual connections that you have there. So it tells us quite a lot about the architecture. It has kind of an interpretation. Okay, now what can we use this for? So one option would be to use the operation counts already as a proxy, which we do if it's an L2 norm. But we could also use this to enhance performance predictors. So we will use that as an architecture encoding, and we will also compare it with zero-cost proxies. So each row here is an architecture, and we collect all the zero-cost proxies that we can get, all the graph features that we can compute, and also for reference, the one-hot encoding. And in all the plots that you will see, it's basically the same procedure. So we will encode the architecture using either only graph or zero-cost proxies or both, or also with one-hot encoding. And then we will sample some training architectures and determine the target, which can be the validation accuracy or some hardware task. Then we'll train a random forest. Later, we also use some XGBoost, but here mostly a random forest because it's fast, so we could do many, many ablations. And then we even have the trained surrogate. We will evaluate it on all the remaining networks in the search space and compute the candle power. Yes, then that's what we did. And here you can see results for 1024 training networks. It's cipher10 and it's 3 different search spaces. So here is NAS Bench 101, then 201 and MB301, which is basically darts or like a subset of darts. And each row is one type of encoding. So the first one is one-hot encoding, then GRAF with unhot encoding, and zeros proxies, etc. What's blue uses GRAF, what's orange does not. And we can see that using GRAF just helps in all the cases. Also, GRAF on its own is better than both one-hot encoding and zero-cos proxy-based encoding. So just getting all those path lengths operation counts just works really well. What we need to note is that zero-cos proxies are not completely useless. First, they are better than the one-hot encoding. Second, if we add them to GRAF, it gets better. The prediction is in all cases is better. I need to move our faces. Yes, even for darts. Even though for darts the zero-cos proxy effect isn't that large, which you can see like just zero-cos proxy on its own is worse than one-hot encoding here. So that was a result we were very happy about. And then we went to the other search spaces. So this is Trans-NAS Bench Micro, which is basically NAS Bench 201 without average pooling. The task is autoencoder, which was kind of specific in the sense that zero-cos proxies didn't have a large correlation on it. And when we use the GRAF encoding here, we found out that it works really well. Please compare it, for example, to the zero-cos proxies. Zero-cos proxies aren't really needed here, so it seems like they don't really capture what's important for the autoencoding. If you want to interpret why GRAF works better on autoencoder than zero-cos proxies, we can look at feature importance. We used SHAP to get feature importance of every feature, like GRAF feature and zero-cos proxy. So it was the same random forest prediction, and I think these were 1000 training networks, and then we would get the feature importance. And what we can see, these are actually this, except the average pooling, same search spaces, but a different task. And for the first one, a lot of the proxies are important, and the second one, NASWOT, so number of convolutions, it's really important. So kind of the proxies overfitted on cipher10 and the number of convolutions because it was important for the task prediction. But if we look at autoencoder, we find out that minimum path length over skip connections is really important. This is also consistent with some line of related work where, I should have put the paper here, but basically the more skip connections the architecture had, the better it was, even though for the other tasks like cipher10, the more convolutions there were, the better usually the architecture was. We see that the zero-cos proxies still have some importance, even in autoencoder. You cannot find NASWOT in the top 10 more important features, so that's kind of the difference. I feel like the zero-cos proxies can still be quite good for encoding in general. Like they won't necessarily correlate with the target, but they can give you some information about how the architectures differ from each other. Okay. Now there will be a lot of slides about all the tasks that we studied. So if you like work on some of these applications, it might be quite interesting for you because there are some differences of what works and what not. In general, for hardware targets, one-hot encoding tends to be quite good. So, for example, here, one-hot and zero-cost proxies are kind of similar. For other tasks, I think it was sometimes even like one-hot was better than zero-cost proxies. Also, like adding flops and params to one-hot encoding will just make it instantly better than zero-cost proxies. So, but nevertheless, when you add GRAF to the mixture, you get quite a good performance. It varies across the hardware tasks. Some were more difficult, so the candle tower was more like 0.8. But here, just jumping to straight perfect performance in not that many networks. It's quite also a good result. Then we had robustness tasks. So here we look at the table instead of box plots to get as many different settings in one slide. So this is an FGSM attack with various degrees of intensity of the attack. Please, Rita, correct me if I omit something. So I think on the right is the highest intensity of the attack, should be so. And it's again like candle over 50 rounds, and we sample either 32, 128, or 1000 networks, and the different encodings. So for robustness, zero-cost proxies seem to be quite important, at least for FGSM. I mean, GRAF is still here in the largest sample size, better than just zero-cost proxies, but still, for example, on the smallest sample size, zero-cost proxies are really good. So there's just a lot of variance depending on what your task of interest is. Also, in general, I think the robustness tasks were quite difficult to predict, so it's also a potential line of research that one could take because it hasn't been studied so much. All right. Then we also compared with other predictors because so far it was just random forest and a bunch of encodings, and surely MLPs or GNNs will be better, right? Well, no. So there was a survey about performance predictor by Colin White and the others, and it was how powerful are performance predictors in NAS. And we used the same setting as the original survey had, only, for example, for MB101, we limited ourselves to those networks that had the zero-cost proxies scores from NASBench to 0. And anything like XGBoost or random forest with GRAF is better than all the other predictors. So actually, SemiNAS was the only one that was comparable in search, but it's a much slower method. Like fitting random forest on zero-cost proxy scores and GRAF is really fast, while running training a semi-supervised model on the whole search space or on a sample of the search space still takes quite a lot of time, and it reaches the GRAF performance just at the very end, and it's still a bit worse. What's interesting also here is that MLP scales quite, like reaches the high performance quite slowly. So it's kind of, we could look at it as kind of a small data problem because we've got just 30 networks at the beginning, and we get quite a good correlation with GRAF and zero-cost proxies, but MLP takes ages to reach there. And also GNNs aren't good here. So all the GNN models are hidden somewhere here. And I mean, it would be great to have better GRAF neural network models because this is still just feature engineering. It's not that flexible. We can definitely do better. We also compared with the path encoding, which was not really better, and also it scales even worse than GRAF. Then with NASBO, it wasn't better, but we didn't use it in the original BO setting. So it might be that when we would combine it actually with the Bayesian optimization, it could be comparable or better. That's an open question. Then we also did quite an extensive set of experiments on BRPNAS, so a GNN model, performance predictor, which can be combined with zero-cost proxies and GRAF quite easily. So we get just the embeddings out of BRPNAS and then concat it with whatever features we have and pass it through a set of dense layers. And this was actually the best result on NASBench 301. So for more complex search spaces, actually combining GNNs and GRAF and zero-cost proxies might be quite good. Which we also saw for TA gates, which is a GNN that's already combined with zero-cost proxies. And on the largest sample size, which is the top row and the red box, it was actually better than GRAF, even though on the smaller sample sizes, it was worse or comparable. So I would say that GNNs are not that either, but they need to be, we need to use either better GNNs or combine them with zero. All right, for context, nowadays with for example, GPT and large language models, a lot of the new search spaces are kind of macro search spaces. So we choose how many heads there are, the number of layers, and that's not really the graph structures that we did here. So we can also think about features in the sense of macro search space. So for trans-NASBench macro, it's basically just a chain search space where you have either normal models or models with dump sampling and channel increasing. And we kind of thought about some macro features which were like also the model count, so number of channel increasing models, but then also how many channel increases have been until a position. So for example, at position 3, we did 2 channel increases or just 1. And this also made the results better. And we can also see that one-hot encoding just doesn't work really well. I mean, maybe it would with an MLP, so it could be a limitation of random forest. But with performance prediction, we usually don't reach that level. We usually don't have that many training networks. So just please, if you have some numbers and you have a choice out of 3 numbers, maybe don't one-hot encode them, but just use a number and see how it goes, if it's better or not. It probably is better. Anyway, I talk about a lot about the pros about GRAF. So one pro that I haven't mentioned is that you don't need to compile the method or pass any batches, which can be quite good if it's, for example, a large model. You maybe don't want to pass anything through it, or maybe it doesn't even fit on your GPU. So that's nice. Okay, it works quite well with zero-cost proxies, and it's also quite nicely interpretable. What's not nice is that you kind of need to adapt it every time. So if you've got a new search space or even a new macro search space, you have to think what to use. So it's not like a nice method that you just use out of the box. Also, it's a question how it works for larger architectures. This was just like a cell. So if you've got a large architecture, maybe the path lengths aren't enough anymore to just describe it. So maybe then you actually need a GNN. But we didn't have any benchmarks to actually use, so it would be nice to look at this. The biggest con is that if you've got a lot of operations, then because of the subsets, this kind of blows up. For darts, it was kind of like 1,500 or so features. That's not that much. But if you add many operations, then it's going to be infeasible to do that. So either you use a subset or actually zero-cost proxies are better. And lastly, transfer across search spaces is easy for zero-cost proxies, not here. Here you can do transfer for different tasks, but not across search spaces. So now, are zero-cost proxies dead? Well, no, because one score can be better than n features. We also saw that you can combine it with GRAF to have it better. And also, it's mostly architecture agnostic. So if you've got a lot of variance between architectures, it can also make it be better. In general, I feel like the research that we have on GRAF should be rather a motivation to find better zero-cost proxies, because that can really help, for example, for the large models, large search spaces. Just having a zero-cost proxy that will help you filter out the search space will help a lot. I think there's quite already at the limit of the talk. No, I can talk. Okay, I've got just a few slides with tips. So let's say you have a new search space and you want to adapt GRAF for it. So if it's already similar to what we have, there's code that you can easily adapt to your search space, especially operation counts are quite easy. So numbers are better than one-hot encodings, just put them in there. What could also be an option, especially for macro search spaces, you could maybe ask an LLM to propose you some features, which we did during the reviewing phase, and that looks actually quite promising. And if you don't do that, then just like sit, look at the data frame, look at the scatter plots, and try to think of some ratios, sums, running sums. It's usually something that your predictor will be very happy about. On the other hand, if you want to adapt zero-cost proxies to your new search space, which I recently did, it's fun. It's tricky. It's so one thing is it requires a backward pass, so it might not be usable. But if yes, then you may need to change a lot in the zero-cost proxy code or your code. But what you can do beforehand is to adapt your architecture in a way that you use layers instead f dot something. So for example, reuse instead of f dot relu, linears instead of f dot linears. And then you have to really look at the code and, for example, some of the proxies replace the forward pass to collect the activations. So then you also need to do that. So in summary, GRAF might be easier in a way that you can just apply it. It's just counting some things. Zero-cost proxy can be really great, but sometimes can be really hard to use. Yeah, and I try to think about how to make it more general, but in some way you can, because if you need to replace the whole forward pass, then the forward pass will differ quite a lot. Maybe you could use an LLM to replace the code. Yes, that's certainly possible, but hopefully it gets it right. On the other hand, if you don't do this, you will sacrifice some performance, some transferability. So in some cases, might be still worth the time to adapting it. All right, so I hope that everybody understands that mass is not dead. We can still speed things up, even for LLMs. For example, you still get some hardware predictors for supernets. We can still use our NAS methods. And I feel like performance prediction is more important than ever, because just getting rid of the really bad networks is really important if you want to save costs. But we should be really sure that we understand well why and how our performance predictors work. And to conclude, one-hot encoding mostly is not enough, as far as I know and my experiments have confirmed. And we should study things like GRAF and how to make other methods better. So thanks for the attention. There's actually a bunch of links. Since I talk quite long, I will not show the code, but you should see it in the video that should be out soon about the performance prediction tutorial. And if there are any nice questions or complaints, I will be happy to answer.